I'd like to thank the organizers for inviting me to talk about this topic. And well, I will try to take inspiration from Andy's excellent talk of this morning. And therefore, I will start my talk by defining the mapping class group. So when I write sigma, for me, it will always be a compact, oriented, and connected surface. Maybe I will allow to have some boundary, so I will write sigma Gn for a surface of genus G and n boundary component. So this is this surface. And for me, the mapping class group of the surface of genus G and n boundary component will be again a quotient of positive diffeomorphism group of sigma Gn by homotopy. So any diffeomorphism that is homotopic to the identity, I will take as trivial in this group. And here, well, the only difference with this morning is that when I have boundary, I will assume that everything here is the identity on the boundary. So my diffeomorphism are identity on the boundary, and the homotopies have to stay equal to the identity during the isotopy. And as we said this morning, we still have the same typical example of elements. So if we have gamma, which is an embedding of S1 times 0, 1 in the surface, we get a twist, which I will write as T gamma in this class. And well, Andy wrote down what this is. Well, you can take T gamma to be the identity on sigma minus gamma and rotation of angle T on S1 times T, 2 pi T. And well, this gives you another definition of the Dehn twist. So the point of this class will be to define and then talk about the properties of some representations of those groups. So what we will talk about are so-called SO3 quantum representations of mapping class group of surfaces. So those are a family of representations depending on the parameter R, which will be an integer, which will be at least equal to 3 and odd. And so for each such parameter, I will get a representation which goes from mapping class group of sigma Gn into the projective. This will be a projective representation, so it goes into PGL D. So D is some integer which depends on N, G, and R of. So here I could write C, or I can be a bit more precise because I know more fields than Andy does. So I know that there is the cyclotomic field. So here, this is the cyclotomic field, and I have that zeta R is the root of unity of order 2R. And here I can alternatively write this as the projective automorphism of some vector space which is associated to the surface. So here this is a vector space over this field of finite dimension and associated to the surface sigma G. Okay, so first a remark. So here there's this I say those are the SO3 representations. And well, later I won't talk about SO3, but I just say a word why they are called SO3. So the fact is that they are part of a more general construction, which takes as input a so-called modular category, which I won't talk about and I won't define. And well, from this you can define various quantum families of quantum representations. We can talk about SU2 representation, SUN. You can talk about SPN maybe, or E8, whatever you want. Like you have kind of one for each compact Lie group. And well, but here we won't talk about those because most properties are shared between each family of representation. They kind of have all similar properties, so why not just look at SO? Okay, so I'm supposed to talk about properties, but the first thing I will talk about will be a non-property. So some property that those representations do not have. And well, this might disturb Andy, because Andy told us that the properties of the mapping class group, when you want to show that a certain property is satisfied by the mapping class group, you want to extract it from an action of the mapping class group on a nice space. And here, well, those, they do not come. They are not constructed using an action of the mapping class group or a diffeomorphism group on a nice space. So, well, that means that those representations are intrinsically kind of weird, kind of awkward. And, well, when you meet someone that is a bit weird and awkward, that doesn't necessarily mean that it's not worth talking to them. It just means that you have to put in effort to get to know them. And so that's what we are going to do in this talk. And it will turn out to be worth it. So, because it turns out that those representations, they have many kind of unique properties among representations of mapping class group. So one property is that they are unitary. So here I say that those are representation in PGLD of, well, I could forget about this field and just say they are in PGLD of C. For that, I need to choose an embedding of this in C. There are several. So when I do that, I get a representation with image in the projective unitary group. So when I choose the embedding into C was, so this is already a kind of special property among representations of mapping class group. They are not the only ones with this property. There is a property which is not necessarily a good one, but which is interesting. Well, they are not faithful individually. So what we have is that when we take a Dehn twist, so for any gamma, a simple closed curve, we have, when we take the Dehn twist T gamma and we raise to the power R, So R is the parameter the integer parameters that gives me the specific representation. Well, when you look at this, it's in the kernel of rho. So faithful, however, they are asymptotically faithful. So here I will write theorem. So you have a theorem which was proved by Friedman, Walker, and Wang. And which I will, for simplicity, only state for closed surfaces. So for, let's say for G at least 3, the intersection of the kernels of rho R is just the identity. So you take all the intersection of all the kernels of those representations, then you will get only the identity. It's actually a bit more precise than that. Whenever you take a non-trivial element, it will not be in any of these kernels for R big enough. Okay, when G equals 2, there is just a little difference, which is that you get the center of the mapping class group of sigma 2, which contains 2 elements. Contains the identity and another element, which I will write as iota, which is the so-called elliptic involution, hyperelliptic involution, which is the following map. So you picture the genus 2 surface in this way, and you put a skewer horizontally through the surface, and you do 180-degree turn. This thing will be in the center of the mapping class group of the surface of genus 2, and it will also be in the kernel of those representations for all R. You can define the representation for G equals 1, or even for G equals 0. Just in that case, you will have a big kernel. For G equals 1, you will have a big kernel. So the asymptotic faithfulness is really for G at least 3, kind of for G equals 2, and not at all for G equals 1.
Is there a way to say what that kernel is?
G equals 1. What you get is sorry. You also have that. Sorry. For G equals 1, you can find the kernel of each of those, and the intersection of the kernel is still 2 elements. But for G equals 1, you have that the kernel of rho R is the kernel of the map from the mapping class group of T2 into, so you have a map onto the homological representation gives you a representation which with values in SL2 of Z, and well, when you model by R, this is exactly the kernel.
So it's the level R.
Yeah.
So that means the intersection is trivial, though, right? The level intersection.
Sorry. Yes. Yeah. Yeah, I assume no boundary components for simplicity, but you have similar statements when you have boundary components. Okay. So, well, this is a nice property of the family of representation. But if we continue talking about properties of each individual representation, we can find the following. They have infinite image. for, well, they mostly have infinite image. This is now a theorem which proved independently by Masborn in 98 and Funar in 98 also at the same time. You have that rho r from mod. I will again write the statement for a surface mostly. So you look at this and I say that has infinite image unless r equals 3. Yeah. Yeah, that's it. So, well, what I wrote was, well, there are closely related, which are the SU2 representation, and there you have more exceptions. So in that case, you would get exceptions which are 3, 4, 6. Like I can allow parameters which are not odd, and in case you get more exceptions. Get those, and you also get the case GR equals 210. Okay, so well, kind of striking property, and gives you as an application a statement which, well, does not involve the quantum representation at all. You can look at a mapping class group of sigma g, and well, as we say, we have some natural elements in the mapping class group which are all Dehn twist, and so there is a natural quotient which is to quotient this group by all powers of Dehn twist of fixed exponent. So when I look at the quotient of this by all half power of Dehn twist, where where gamma is a simple closed curve, well, I get that this group is infinite, except for the exceptions that I wrote here. So except for r equals 3, 4, 6, also GR equals 210. Yeah, here I might have to add multiples, so 12. For the SU2 version, where I allow even parameters, I have to multiply the order of the root by 2. So this is why it does as 12. Okay, so we see that using those strange representations, we can get some applications which are a priori difficult to tackle directly. Well, they were first discovered this way, and I think this one now is an independent proof. But here you see that you know that the representation has in its kernel all half power of Dehn twist, and you know that except for those exceptions, the image is infinite. Well, that tells you that this quotient has to be infinite, because you can think of the representation as being defined on this quotient, since all of those are in the kernel. Okay. Listing some properties. So, well, when we have representation, it's natural to ask about whether they're irreducible or not, whether you can break it down into simpler representation. And here what we know is that so rho r is irreducible if r is prime. If my parameter is prime, the order of my root of unity is prime number. I know that this thing is irreducible. This was proved by Roberts, I think in 1909. And well, if R is not prime, not much is known, but there are some things that are known. So you can, for example, have R equals product of two primes. Two distinct primes. Or, yeah. So this was by Korenman around 2015. There's also another case similar to this for the SU2 representation. But otherwise, in general, we don't know when exactly they are irreducible or not. It's expected that they are most of the case irreducible. In most of the cases. Okay. Sorry? Well, no, you don't know whether they are indecomposable too. Like it's yeah. They're unitary for some choice of embedding. So yeah, if they were, they would be also reducible. Okay. So well, what else? Again, when R is prime, we have extra properties that we're able to say, to find. So if R is prime again, they are integral representation, meaning so it's a theorem by Gilmer and Masbaum from something like 2007. Well, up to a suitable choice of conjugate, you can say that rho R has image in. So again, projective linear group, but with coefficient in the cyclotomic ring instead of the cyclotomic field. So so this is nice because you have a ring here, you can take an ideal in this ring, and you will extract from the quantum representation many representations into finite groups. And well, as an application of that, you can get following theorem of Masbaum and Reid from 2008, I think, which tells you that in a way that you can find many finite groups inside the mapping class group. So there is this notion of a group being involved in a group, another group. So I will write the statement and then I will explain. So the statement is that all finite groups are involved in mapping class group of sigma G, where G is like is 3, let's say. What does involve mean? So for any G, a finite group, there exists gamma, a finite index subgroup inside the mapping class group of sigma G, and a map, a surjective map from sigma to G. So it means that any finite group is a quotient of a finite index subgroup of the mapping. Okay, so this is interesting property that you can derive from this fact that the quantum representations are integral, and that you can, by quotienting by an ideal, define many representations inside finite groups. For each fixed genus, yes. Yeah, it's much easier. Yeah, in fact, yeah, if you're allowed to take all genera at once, you can look at the, so you always have the so-called homological representation. So you have that the mapping class group of sigma G as a representation into the automorphism of the H1 of sigma G with coefficient Z. So this is just because the diffeomorphism group acts on the surface, and thus you can extract an action on the homology. And because of that, well, this will be this is the same as the symplectic group in Z. And this is also a surjective map. And if you're allowed to take all genera, then you will be able to find your subgroup here. After taking, well, you also have a map into SP2G of Z over LZ. And you will be able to construct your finite group that is involved in some mapping class group. But if you fix G, then it's much harder. Okay. Well, and finally, another property that well makes us interested in those quantum representations. They don't exist in a vacuum. They are related to many invariants of free manifolds and of links. So you can say that the representation rho are actually coming from the TQFT, which I will write as RTR. So I won't explain in full detail what's a TQFT, but what this means is that you have this RTR, which is a functor from the so-called category of cobordisms of dimension 2 plus 1. So what does it do? For any surface sigma G, you will get a finite dimensional vector space. RTR of sigma G, together with a Hermitian form. For any free manifold M, you can associate an invariant, which is RTR of M. It's a complex valued invariant, or I could say an invariant valued in the cyclotomic field. And for any M, which is cobordism from sigma 1 to sigma. So what does this mean? This means that the boundary of M is the union of two things, a copy of sigma 1 and a copy of sigma 2 with the opposite, sorry, to write like copy of sigma 1 with opposite orientation and of sigma 2. And you can think of it as looking like this, like you have an incoming boundary and an outgoing boundary. This would be sigma 1 and sigma 2. Well, whenever I have such a cobordism, I get a map, a linear map. RTR of M, which goes from RTR of sigma 1 to RTR of sigma 2. Okay, so this is, well, very loosely speaking, what the TQFT is about. There are more actions, but I won't tell you about all the actions. Well, there's one important axiom is that when you pose linear maps, the way you define this linear map from the cobordism, they are compatible with composition. So when you have when you have a first cobordism from sigma 1 to sigma 2, and a second one from surface sigma 2 to sigma 3, or you can glue them together on this boundary component. And well, you get a cobordism now from sigma 1 to sigma 3. And well, the linear map that you get then is just the composition of linear maps. You have that RT-R of M is the same as linear map that I obtained from gluing onto sigma 2. Here, notice that to make sense of this gluing, I need to have a way to identify those two boundary components. And actually, in a cobordism, you also fix a way to identify each boundary component with a standard surface of the correct field. Okay. So this is a list of properties that we would like to see during this class. And well, if you look at my notes, I don't have any time markers, and I also have no discipline, so I don't guarantee that you will see all of this. But in principle, that's what we should see during this class. But first, we have kind of a long road in order to just define the invariants. So as I said, it takes some effort to get to know those representations. But here are the 3 steps that we'll have to go through. So we'll have to first define an invariant of links, of frame links. So which is called the Kaufman bracket, and which is, if you heard that word before, closely related to the polynomial of links. Just it's a framed version. And out of that, using this invariant of links, we will find an invariant of free manifold. So this is the invariant that I was writing here, the invariant RTR of M, which is the so-called Reshetikhin-Turaev invariant. And well, it was defined mathematically by Reshetikhin-Turaev, I think in around 92, but before them, Witten gave a heuristic definition of those invariants. It was around 89. So they are called Reshetikhin-Turaev invariants, or sometimes Witten-Reshetikhin-Turaev invariants. So we will need to define them. And then, as the last step, we will see a process to try to define a representation of mapping class group based on an invariant of free manifold. So then we will do what's called the universal construction. Which is a process that was introduced by Blanchet, Hamegger, Masbohm, and Vogel. Here, I think well, the paper is 95, it was probably before, which extracts a representation of mapping class groups from an invariant of free manifold. So of course, this process is something that does not necessarily give you an interesting representation. But in our case, it will turn out to give us both nice representation. So depends on the invariant whether what you get is interesting or not. Okay, so are there questions so far? So, well, you can define something. It's not like you can define a representation. It's not necessarily finite dimensional. It could be also a fairly trivial representation, maybe one-dimensional, or it could even be zero-dimensional, what you get. But just you have this construction, and sometimes it works, sometimes it does not give you a nice representation, but here it will. Okay, so this was the end of my introduction, and now I will focus on defining this first ingredient. So we'll talk about Kaufman bracket and also scale modules of free manifold. Okay, so when I have M, which is a free manifold, I don't write it, but it's again oriented, compact. What I call a link in M will be an isotopy class of embeddings of a disjunct union of copies of S1 into M. So you can have some number of copies. And I also would like to talk about frame links in M, and in which case I will thicken a little bit the component, and I will take an embedding of annuli into M, disjunct union of annuli. An isotopy class will just mean that, well, if you have an homotopy of embeddings, then you consider it's the same thing. Okay, and here you have possibly M equals 0, in which case you say that your link L is the empty link. So you allow this thing. It's an acceptable link too. When you consider the simplest manifold, when M is S3, you have that the frame links have the diagram. Which means that, well, you can do some kind of generic isotopy and then take the projection on R2 and keep an information about the over and under crossing. So this is something very standard. So this would be a possible link. And when I want to have diagrams of frame links, then I have the usual convention that I can think of this this knot into a frame knot as a frame knot by just taking the so-called blackboard framing. So I think that the projection, well, when I see this trend, I think that there is actually a nice parallel that is drawn on the blackboard like this. And well, you have a theorem, which is the so-called Reidemeister theorem, which tell you when are two links, two diagrams of links the same link. So you have that D and D prime are diagrams of the same frame link if related by the moves. So you have first move, which is, well, if you have straight strand, you can add two kinks going in opposite direction, like this or like this. And if that's the case, well, you can straighten your strand, even if your strand is really it's really a little ribbon like this, you will still be able to straighten it by an isotopy. So this is the first move. Second move is when you have two strands that have two crossings like this, you can make them disjoint. And the third one is when you have three strands, two of them make a crossing, and there's another one that goes, for example, behind. Well, you can move this below the crossing. Okay, and well, you have variants of this one. You can put the strands here in several similar position. Like I could put this horizontal strand on top. Would be also Reidemeister 3 move. Okay, so this is the Reidemeister theorem, and from this theorem we can construct. We'll use this theorem to construct an invariant of links in S3, of frame links in S3. Yes? Yeah. Yeah, you're right. I should have done it like that. Oh yeah. Ah, yeah. Yeah. Yeah, so I was saying that you can define an invariant of frame links using this. So I say that there exists a unique invariant, which I will bracket L of frame links in S3. Satisfying following. Well, first I want that the empty link has invariant 1. Secondly, I want that when I take the disjoint union of a link and an unframed unknot, then it multiplies the invariant of L by this quantity. And finally, when I have a link which in a certain ball presents a crossing like this, then I can resolve this crossing and express the invariant of this link in terms of two over links, which are the same except in the same small ball. So here, there are three links which differ only in a small ball. And here I have a crossing, and in the other two I have those there.
So is it, what is this invariant?
So the invariant lives in the Laurent polynomials in the determinator. Okay. Well, and here, well, you can easily see if the invariant exists when you have if D is a diagram for L. You will have that the invariant for L is be the invariant of the diagram. When I have a diagram, I can use this relation to erase all the crossing and express everything in terms of links that have no crossing. And then I can erase those components, those trivial components that remain. And I will get, in this way, a formula that depends only on the diagram. So I will have that I can choose two ways of resolving each crossing. So I take it as having a map from the set of crossings of D into plus or minus 1. And if I take a positive resolution, I will multiply by, I will have a factor A, and else I will have a factor A inverse. So I will get here factor looking like this. And then I will have to erase all the trivial components. So here, this depends only on my resolution. Here, this would be the number of trivial components I get. And so this would be the formula for the invariant. And it turns out that, well, once you have said that, it shows that the invariant has to be unique, but you don't know that it's invariant. In fact, it is. And you can show that it's invariant under Reidemeister rules. Okay, and I will just do the example of the first move, and I will leave the other moves as exercises. So if you want first move, well, I can try to express this in terms of the straight strand. Here, if I resolve this crossing, I will see that I have, I have two kinks. I will first do a computation involving one kink, and then I will get the invariance for the two kinks. So I get this plus A inverse times this guy. And here I get a trivial component, so I can erase this. And here I get, in the end, A times minus A squared minus A minus 2 plus A inverse times, it's always the same thing, a straight strand. And here, well, it turns out that this is minus A3 times. And if I had put the kink in the other direction, I would get minus A to the minus 3. So when I have the two kinks, the multiplicative factor that I get here compensates. And so it's invariant.
So is there a parenthesis around that following up the second line?
Yeah, A times this guy plus A inverse. Yeah, it's like that. So as I said, for this guy, you would get minus A minus 3 times this. So this will be invariant under the first move. The other calculations are similar, and well, the second one is not very long, and the third one, because there are so many variants, a priori you would have to do a lot, but but nothing is hard to do. Okay, so well, I want to kind of generalize this invariant into an invariant of kind of manifolds and links in three manifolds, and I will talk about skein modules. So we'll define this notion, and well, this notion will be important because the space that we say that our quantum representations are I've imaged in automorphism of some vector space with RTR of sigma. And this RTR of sigma will be a quotient of such a skein module. So that's why both things will be important. So I take M a free manifold, and well, I can also take P to be a union of intervals embedded in M. So in boundary of M. So it could look like this. I have my manifold M here, and I want to have some little intervals embedded in the boundary. I say that the skein module of M with boundary points P will be obtained in this way. So I take the Z A inverse free module with generators frame tangles in M with boundary equals to P. So here a frame tangle, it's well similar to the notion of frame link. I will embed some annuli in my free manifold, but I will also embed some squares, like product of two intervals. And I want that the boundary is on my set of intervals P. So the boundary of my frame tangle is a disjoint union of intervals in the manifold that I fix to be P. So
you can't have two of the frame tangles in the same interval without happening. Take up the entire.
Sorry, say it again.
So your frame tangles, when they hit the boundary, they have to take up an entire interval. It's not like you take up part of it.
Yeah. Okay. They take the entire interval. Okay, so here I'm just defining a free module, so it's not very interesting, but I will add some relations, and the relations that I will add are the relations that are satisfied by the Kaufman bracket. So I will say that relations K1 and K2 of the Kaufman bracket. So whenever I have a link in M or tangle in M disjoint union with non-naught, well, I say that I just multiplied my element by minus a squared minus a minus 2. And
how's the framing work?
the unknot has to be a non-framed unknot. Yeah, sorry. So
the framing has
is important. Yeah. If I change the framing, because of the relation we see here, we will multiply this by a power of minus a third.
We don't need to be like homologies here to make sense of that.
No, we don't need to. Like all I want here, this unknot lives in a small ball, so I know what is an unframed unknot inside the small ball. And well, we have the other relations that tells us that if in a small ball you see a crossing, so again, you could say, well, what is the notion of a crossing inside a free manifold? Yeah, I'm just saying, well, in a small ball I see this picture. Then I say that this is equal to this plus this. And here it's important that the manifold is oriented. If it's not, then I have no way to distinguish between this version of the crossing and the negative crossing, but I should have different coefficients in the other case. So I have to have that my manifold is oriented. Sorry? P? P has to be even, otherwise, yeah, I don't have tangles with boundary P. Yes?
Oh, you demand your tangle take up the entire thing. It's not
Yeah. And yeah, there's no Möbius band. Yes.
Sorry.
Yes.
If you're talking about like a general free manifold rather than just like S3, how are you defining the Kaufman bracket without diagrams?
I'm not defining a Kaufman bracket. I'm just saying that here I had this free module, and I'm saying that I have the same relation as the Kaufman bracket, meaning that I will impose the following relation, that if I have a linked disjoint union of unframed or not, then in my scale module here, it should be equal to this, to the same link times this coefficient. So yeah, so yeah, this is relation K2 and K1 and K2.
So there's, I guess, the difference between S3 and this is that I guess in S3, this leads to like a well-defined single. Oh no, this could be trivial.
Yeah. You don't know whether this module is trivial or not. Well, in many cases we know it's not. Like for any rational multisphere, closed rational multisphere, we know it's not trivial, but we don't even know that it's trivial in it's non-trivial in all generality. Okay, can give some examples. Well, the first example is the one we already gave, which is S3. So when we have S3, it turns out that the scale module of S3 is just ZAA inverse. Well, because well, whenever you have a link in S3, you can again erase all the crossing, erase all the trivial components, and you will get that in the scale module, any link will be a multiple of the empty link. And furthermore, you know that the Kaufman bracket gives you a map from this to ZAA inverse, so you need to have this to be isomorphic. And in general, when you take to be a thickened surface, sigma times 0, 1, you will have that S of so f of sigma times 0, 1, which I will write as just S of sigma most of the time, is a free module generated by multi-curves on sigma. So those are disjoint union of simple closed curves on sigma.
So is there no, like, if you have like two multi-curves with unions of multi-curves, there's no relationship between those generators? They're totally independent?
It's the multi-curves give us a basis of this game.
Now the curves in a multi-curve are non-trivial, like you got this?
Yeah. So multi-curves, disjoint union of simple closed curves, all essential, all non-trivial. And here I also have to allow the empty multi-curve. Sorry?
So those will be simple.
Ye-
Yeah, those will be like all over the surface, right? There's like billions of times.
So maybe I draw a multi-curve just to such that we agree. So so that we agree. So a multi-curve will be just. So I want to have some number of simple closed curves. Maybe I take this one, and then I can take several parallel copies of the same one. It's perfectly allowed. So here this is an example of a multi. Okay. So another example will be handle body. Of genus G. So the definition of a handle body of genus G, you can think of it as taking a ball B3 and then gluing several copies of, this is D2 times interval, onto the ball. So if you glue G copies of D2 times interval onto B3, you get the handle body of genus G. But here you can also think of this as the disk minus with G holes, so the surface sigma 0G times an interval. And so again, the handle body of genus G will be a free module. So here you can think of this. You see it from this picture that we just take this guy and we thicken and we'll get a handle body of genus. So again, the handle body of genus G will get a scale module which is a free module. It will turn out that the way we will define the space RTR of sigma G, it will be defined as a quotient of the space. Sigma G plus 1, yes. Yeah, it would be the disk with G holes, but the sphere with G plus 1 holes. Okay, and well, maybe I'll finish here. It's already 1 hour.